When dealing with a 30 amp 480 volt single-phase load fed from a 2-pole 30 amp breaker, and considering an 850 foot run using number 3 THHN conductors for the ungrounded conductors, the question arises about the appropriate size for the equipment grounding conductor, or EGC, as required by the National Electrical Code, NEC. The NEC dictates the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device protecting the circuit. In this scenario, the overcurrent protective device is a 30 amp breaker. To determine the correct EGC size, one must refer to NEC Table 250.122. This table provides the minimum size of equipment grounding conductors for grounding raceway and equipment. It correlates the size of the overcurrent device with the required EGC size. According to NEC Table 250.122, for a 30 amp overcurrent device, the minimum size of the equipment grounding conductor is number 8 copper. Therefore, a number 8 copper conductor would be required for the equipment grounding conductor in this situation. It's important to understand the function and importance of the equipment grounding conductor. The EGC provides a low impedance path for fault current to return to the source. This low impedance path facilitates the quick tripping of the overcurrent protective device, such as the circuit breaker, in the event of a ground fault. By quickly clearing the fault, the EGC helps to minimize the potential for electrical shock and equipment damage. The NEC specifies minimum sizes for equipment grounding conductors to ensure that they can safely and effectively carry fault current. Using an undersized EGC can result in a higher impedance path, which can slow down the tripping of the overcurrent device and increase the risk of electrical hazards. When selecting the equipment grounding conductor, one must also consider the material of the conductor. Copper and aluminum are the most common materials used for EGC. Copper is a better conductor than aluminum and therefore requires a smaller size for the same ampacity. However, aluminum is less expensive than copper, which can make it a more attractive option in some applications. If using aluminum, the NEC requires that the EGC be size larger than a copper EGC for the same overcurrent device rating. This is because aluminum has a higher resistance than copper. In this case, since we are specifying a number 8 copper conductor, we need to verify if using an aluminum conductor would necessitate a larger size based on NEC Table 250.122. If the table indicates a larger size is required for aluminum, that size must be used. The length of the circuit run does not directly affect the minimum size of the equipment grounding conductor as determined by NEC Table 250.122. However, voltage drop calculations are essential for the ungrounded conductors to ensure adequate voltage is delivered to the load. In this case, voltage drop was considered, resulting in the selection of number 3 THHN conductors for the ungrounded conductors. While voltage drop considerations influence the size of the ungrounded conductors, they do not change the minimum size requirement for the equipment grounding conductor, which is based solely on the rating of the overcurrent protective device. It's also important to consider the type of wiring method used. The NEC provides different requirements for EGC depending on whether the wiring is in metallic conduit, non-metallic conduit cable, or other wiring methods. For example, if the wiring is in metallic conduit, the conduit itself can serve as the equipment grounding conductor, provided that it meets certain requirements outlined in the NEC. However, if the wiring is in non-metallic conduit, a separate equipment grounding conductor must be installed. In this scenario, assuming a separate equipment grounding conductor is required, the number 8 copper conductor would be installed alongside the number 3 THHN ungrounded conductors within the conduit. Proper installation of the equipment grounding conductor is crucial for its effectiveness. The EGC must be securely connected to the equipment enclosure and to the grounding electrode system. The connections must be made using approved methods and materials to ensure a low impedance path for fault current. The NEC provides detailed requirements for grounding and bonding, which must be followed to ensure a safe and effective electrical system. It is also important to consult local codes and regulations, as they may have additional requirements beyond those specified in the NEC. Local jurisdictions may amend or supplement the NEC to address specific local conditions or concerns. When working on electrical systems, it is essential to prioritize safety. Always de-energize the circuit before working on it and use appropriate personal protective equipment, PPE, such as gloves and safety glasses. If you are not qualified to perform electrical work, it is best to hire a licensed electrician. Working with electricity can be dangerous, and it is important to take the necessary precautions to protect yourself and others. Furthermore, it is vital to remember that the NEC is a minimum standard. In some situations, it may be necessary to use a larger equipment grounding conductor than the minimum size specified in Table 250.122. This might be the case if there are concerns about voltage drop on the grounding conductor or if the equipment manufacturer specifies a larger EGC. Always refer to the equipment manufacturer's instructions and specifications for any specific requirements. In summary, for a 30 amp 480 volt single phase load fed from a 2-pole 30 amp breaker with an 850 foot run using number 3 THHN conductors for the ungrounded conductors, the NEC requires a minimum of number 8 copper for the equipment grounding conductor. This determination is based on NEC Table 250.122, which correlates the size of the overcurrent device with the required EGC size. Remember to always consult the latest edition of the NEC and any applicable local codes and regulations to ensure compliance. Also, prioritize safety when working with electrical systems and seek the assistance of a qualified electrician if needed. One must not only consider the size of the equipment grounding conductor, but also the method of connection and the overall grounding and bonding system. The grounding electrode system, which typically consists of ground rods, ground plates, or the building's metal frame, must be properly installed and connected to the equipment grounding conductor. The purpose of the grounding electrode system is to provide a low impedance path to earth, which helps to stabilize the voltage on the electrical system and provide a path for fault current to flow back to the source. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electrical shock. The NEC provides detailed requirements for bonding, including the types of bonding conductors that must be used and the methods of connection. When installing equipment grounding conductors, it is important to avoid creating ground loops. A ground loop occurs when there are multiple ground paths between 2 points, which can cause circulating currents to flow in the grounding system. These circulating currents can interfere with the operation of sensitive electronic equipment and can also create a shock hazard. To avoid ground loops, it is important to ensure that there is only one ground path between any 2 points in the electrical system. In addition to the NEC requirements, there may be other standards and guidelines that apply to the installation of equipment grounding conductors. For example, the Institute of Electrical and Electronics Engineers, IEE, publishes standards on grounding and bonding, which provide more detailed guidance than the NEC. These standards can be helpful in designing and installing complex electrical systems. Finally, it is important to remember that electrical codes and standards are constantly evolving. The NEC is updated every 3 years, and it is important to stay up to date on the latest requirements. Changes to the NEC can affect the size and installation of equipment grounding conductors, so it is important to be aware of these changes. Continuing education and training are essential for electrical professionals to stay current on the latest codes and standards. By following these guidelines, you can ensure that your electrical system is properly grounded and bonded, which will help to protect people and equipment from electrical hazards. It's not just about meeting the minimum requirements, it's about creating a safe and reliable electrical system. In addition to the information already provided, it's beneficial to elaborate on specific scenarios and considerations that might influence the selection and installation of the equipment grounding conductor (EGC). Firstly, consider installations in healthcare facilities. Healthcare facilities have stringent requirements for grounding and bonding to protect sensitive medical equipment and patients. The NEC Article 517 addresses healthcare facilities and may require additional measures such as redundant grounding or isolated ground systems. In such cases, the EGC size might need to be increased beyond the minimum specified in Table 250.122 to ensure adequate performance and minimize the risk of electrical noise or interference. Secondly, when dealing with sensitive electronic equipment, such as computers, servers, and control systems, a dedicated equipment grounding conductor may be necessary. This dedicated EGC provides a low impedance path for fault current and helps to minimize electrical noise that can disrupt the operation of the equipment. The size of the dedicated EGC should be based on the manufacturer's recommendations and the requirements of the NEC. Thirdly, consider installations in corrosive environments. In corrosive environments, such as chemical plants or coastal areas, the EGC must be protected from corrosion. This can be achieved by using corrosion-resistant materials such as stainless steel or copper with a protective coating. The size of the EGC may also need to be increased to compensate for any reduction in conductivity due to corrosion. Fourthly, in long circuit runs, voltage drop on the equipment grounding conductor can become a concern. While NEC Table 250.122 provides the minimum size for the EGC, it may be necessary to increase the size to minimize voltage drop and ensure adequate performance. The voltage drop on the EGC should be calculated and compared to the manufacturer's recommendations. Fifthly, when using flexible metal conduit FMC or liquidite flexible metal conduit LFMC as a raceway, the NEC has specific requirements for the EGC. In some cases, the FMC or LFMC can serve as the EGC, provided that it meets certain requirements. However, in other cases, a separate EGC must be installed inside the conduit. The size of the separate EGC should be based on NEC Table 250.122. Sixthly, in high-noise environments, such as industrial plants with heavy machinery, the EGC can be subject to electrical noise. This noise can interfere with the operation of sensitive electronic equipment. To minimize noise, it may be necessary to use shielded cables or install filters in the EGC. Seventhly, when dealing with multiple circuits in the same raceway, the NEC requires that each circuit have its own EGC. The size of each EGC should be based on the rating of the overcurrent device protecting the circuit. Eighthly, it is important to properly label the equipment grounding conductor. The NEC requires that the EGC be identified by a continuous green color or a green color with one or more yellow stripes. This labeling helps to ensure that the EGC is not mistaken for a neutral conductor or a hot conductor. Ninthly, when making connections to the equipment grounding conductor, it is important to use approved connectors and methods. The connections must be tight and secure to ensure a low impedance path for fault current. The NEC provides detailed requirements for making connections to grounding conductors. Lastly, it is important to inspect the equipment grounding conductor regularly to ensure that it is in good condition. The EGC should be checked for signs of damage, corrosion, or loose connections. Any problems should be corrected promptly to ensure the continued safety and reliability of the electrical system. These additional considerations highlight the complexity of equipment grounding and the importance of following the NEC and other applicable standards. By carefully considering these factors, you can ensure that your electrical system is properly grounded and bonded, which will help to protect people and equipment from electrical hazards. Furthermore, when working with electrical systems, especially at 480 volts, it's crucial to have a thorough understanding of safety procedures and the potential hazards involved. Firstly, always ensure that the power is disconnected before working on any electrical equipment. Use a properly rated voltage tester to verify that the circuit is de-energized. Secondly, wear appropriate personal protective equipment, PPE, including insulated gloves, safety glasses, and appropriate clothing. Thirdly, be aware of the potential for arc flash. Arc flash is a dangerous phenomenon that can occur when electrical equipment is energized. It can cause severe burns and other injuries. Always maintain a safe distance from energized equipment and use arc-rated PPE when necessary. Fourthly, follow lockout/tagout procedures to ensure that the power remains off while you are working on the equipment. This involves placing a lock and tag on the circuit breaker or disconnect switch to prevent it from being accidentally turned on. Fifthly, be aware of the potential for electrical shock. Electrical shock can occur when you come into contact with energized electrical equipment. It can cause serious injury or death. Always use caution when working with electricity and avoid contact with energized parts. Sixthly, inspect all tools and equipment before use to ensure that they are in good condition. Do not use any tools or equipment that are damaged or defective. Seventhly, be aware of the potential for static electricity. Static electricity can build up on your body and can discharge when you touch electrical equipment. This can damage sensitive electronic components. To prevent static electricity, wear a static discharge wrist strap. Eighthly, follow all applicable codes and standards. The NEC and other codes and standards provide detailed requirements for electrical safety. Always follow these requirements to ensure that your work is safe and compliant. Ninthly, be aware of the potential for fire. Electrical fires can occur when electrical equipment overheats or when there is a short circuit. Have a fire extinguisher readily available and know how to use it. Lastly, if you are not qualified to perform electrical work, do not attempt to do so. Hire a licensed electrician to perform the work for you. Working with electricity can be dangerous, and it is important to have the necessary training and experience to do it safely. These safety procedures are essential for protecting yourself and others from electrical hazards. Always follow these procedures when working with electrical systems, especially at higher voltages such as 480 volts. Remember, safety should always be the top priority when working with electricity.